Hi everyone, my name's Tommy Wong and I'm a senior in nuclear engineering and radiological sciences. My specialization within the honors program is research, and my research conducted with Professor Kevin Field of the Nuclear Engineering Department is to investigate FeCrAl alloys for accident-tolerant nuclear fuels cladding with the You Only Look Once Microscopy Edition network, or YOLOME. I was fortunate enough to be a part of this project because of my previous summer experience working on using analytics models to analyze materials at the Oak Ridge National Laboratory. And I intend to carry out a similar line of research in my graduate studies.
So as I have said, my project is on investigating the use of FeCrAl alloys for accident-tolerant fuel cladding with the YOLOME network. So why do we need a new nuclear fuel cladding material? Well, current nuclear fuel cladding materials are made out of zirconium alloys, and when it reacts with high temperature steam, such as during a loss of coolant accident or LOCA, it rapidly oxidizes and releases hydrogen, which, given enough concentration, could lead to an explosion, such as the one in Fukushima Daiichi back in 2011. As you can see in the picture on the bottom showing a reactor without a roof. So FeCrAl alloys or iron chromium aluminum alloys are promising cladding materials because they have a much lower hydrogen liberation rate of about 1,000 times less, and therefore they're being investigated to be used as cladding material for accident-tolerant fuels. But as with most metals, FeCrAl can be damaged and will be by neutron radiation during the normal operation of a nuclear reactor. And when neutrons knock the atoms within the FeCrAl alloy off where they should be, that forms dislocation loops, as you can see in the picture on the right. The little black dots are essentially loops formed by atoms which are knocked off their place, and also the vacancies formed due to atoms being knocked away. And as you can see that with an increasing radiation dose, the density of the dislocation loops and their sizes actually increases. So this poses a problem when the material is being used within a nuclear reactor as a fuel cladding. So to simulate neutron irradiation, we can do that by an ion beam irradiating a sample, such as the ion beam laboratory here at Michigan on the Bible. And the effect of the ion beam irradiation on the sample can be observed using a transmission electron microscope, or TEM, and YOLOME assists in the examination of TEM data. So why do we need YOLOME? Why are we developing it? Well, real-time identification of defects is very important because it allows us to see how they're formed, and from that we could infer formation mechanisms and the morphology and development of such defects. And it also has been shown in other fields that the real-time identification of features in microscopy can be very useful and successful, such as the GIF on the bottom showing cellular structures being identified in an optical microscope. So going a little bit deeper into how computer vision actually works, well, it typically works through machine learning or deep learning, and it involves feeding an image through what is known as a convolutional neural network, or CNN for short, and having the network identifying and classifying that image into one of the classes that it's been tuned to. And within the convolutional neural network, there are typically convolution layers and also max point layers. Convolution layers aim to extract high-level features. As you can see on the GIF on the left, as the kernel or filter scans through an image, it sums up the pixels that are within that filter and assign a value to it. This eventually downsizes the image itself, extracting features such as curves or edges. On the other hand, max pooling layers are used to find dominant features because when they're being scanned through an image, it extracts the highest pixel value from it and assign it to a new matrix, essentially downsizing the image and reducing the computational load of the network in general. The YOLO network similarly has 106 layers of convolutional layers. It also has residual layers, which allows convolutional layers to skip over the next several convolutional layers and essentially providing shortcuts within the algorithm to improve the accuracy and also increase the speed of the network. So the training data for the neural network is provided by Professor Dane Morgan's team at the University of Wisconsin-Madison, and they're in the form of pictures of individual dislocation loops being encircled by a bounding box, essentially a rectangle that takes a snippet of the dislocation loops, and that involves identifying both the coordinates of the loop within a larger picture and also the dimensions of that bounding box. And you could see an example of a bounding box in the right hand side in the image below, where a person and a dog and a sheep are being bounded. The number refers to the confidence that the network believes that the picture that it's seeing refers to these classes. So to create our pipeline for the YOLOME network, we intended to prepare and irradiate FeCrAl samples using the krypton and helium beamlines available at MIBLE to simulate irradiation damage. We'll then examine the sample using the TEM as the sample is being irradiated. We'll then transmit concurrently the images captured from the TEM to the YOLOME mainframe to perform classification of the dislocation loops, and then feed those classification loops back to the user in real time. But due to the closure of the lab, we're only able to prototype the irradiation experiment by using previously recorded videos and capturing a screenshot of the video at regular time intervals to simulate what we are anticipated to do with an actual sample being irradiated. So this is a video of one of the simulated samples being irradiated. As you can see in the beginning, there are some discrepancy by the network classifying small defects and misclassifying some of the background features as the defects. And this is primarily due to the small size of the defects. But as the defects grow in size due to radiation dosage, the network is much more accurate in terms of classifying the defects from the background. And you could see that on these images where the number of defects detected plotted against time, the number of defects increase with time or with dose essentially. They're plotted on two separate images because the imaging area of the left plot is 4 times that of the right. And another thing you could observe is also that as the chromium content increases, the number of defects actually decrease, and that supports a previous study conducted on FeCrAl alloys. One thing you might notice is that there are spikes in the earlier onset of the radiation experiment, and that, as previously explained, is likely due to the confusion between background visual artifacts and the small size defects, therefore seeing several spikes in the early onset. But as the defect sizes increase, these artifacts are all distinguished from the actual defects by the network. And it shows that the YOLOME network is accurate towards the end in identifying the defects, and it also allows a much more rapid analysis. It's almost instantaneous when it comes to classifying these defects when compared to doing that by hand using the ImageJ's imaging software suite. So in conclusion, YOLOME was able to identify these defects on in-situ irradiation TEM videos of FeCrAl alloys rather successfully, and more importantly, it was able to identify them on the fly and at a much higher rate than by hand. So that facilitates the rapid detection of irradiation-induced defects, and in turn, that accelerates the development of accident-tolerant fields when it comes to using FeCrAl alloys as the cladding for such fields. And there are several future work that we have to do. That involves integrating the YOLOME network with the actual MIBO beamline and in-situ irradiation TEM. So that involves creating a script on the TEM software to capture images at regular intervals, such as how we simulated it in the current prototype. We also have to connect the shared folder of the YOLOME framework with the TEM mainframe so that there's a place for the TEM to drop images to and allow the YOLOME network to take these images and perform classification instantaneously. And we also aim to evaluate the accuracy of YOLOME, and more importantly, to improve the accuracy of the YOLOME, especially in the beginning of the irradiation cycle, so that there's a greater distinction between the defects and the background artifacts. And this is the end of my presentation. Thank you, and I look forward to any questions that you might have.